Section 7 is called exponential growth and decay. Exponential growth and decay just uses exponential functions like you learned in the last section. Except now we're going to be talking about like more real world stuff, and that usually means more story problems, which isn't that scary. It's not scary. No, it's not. It's not that bad. Yeah, so in this section we're using exponential functions and apply them to real life situations. We're working with what's called exponential growth. Exponential growth is like interest in a bank account, and exponential decay, like half-life. You guys have heard of those before, right? Exponential growth, like interest in a bank account. I'm sure a lot of you have bank accounts that have interest, and you're kind of making your money grow. That's kind of nice. It's free money. Half-life is like if you have something that's radioactive, it slowly decays over time. It's kind of an interesting thing. You can study it in science a little bit. But like radioactive things become less radioactive over time because they're decaying. Okay, so the first thing we need to talk about is what is exponential growth? And if you look at that graph, you can see that it looks just like what we were doing in the last section. That's because it is just like what we were doing in the last section. We still have this little equation sitting here, y equals a times b to the x power. It's the same as last section. We have this graph sitting here. If we're talking about exponential growth, then we should see a graph that's going up as time goes on. If we were talking about something that goes like this, that wouldn't be exponential growth. That would be something different. So exponential growth can be modeled by the function y equals a times b to the x. The same thing as last section. A has to be positive, so you will not see a negative sign out here. B also has to be greater than 1. And we talked about that in the last section. If b is greater than 1, then we see a graph that looks like this. If b is between 0 and 1, then we see a graph that does that. That's not growth. We'll talk about that later on. That's decay, actually. So I don't want to see this line on here because I don't want to confuse you guys. But that's what we're dealing with. B has to be greater than 1. A has to be positive. Which is kind of nice. It narrows down what we're dealing with. So A is the initial amount right here. Initial amount. When x is 0, or when time is 0, when we have our first starting value, it's sitting right here. That's what A is. We talked about that in the last section also. The base, B, is greater than 1. We talked about that just now. That's the growth factor. And we talked about that in the last section. If we have a population that's doubling, then we'll see a 2 there. Like with the rabbits problem, the population triples, we'll see a 3 there. So it's not a coincidence what these numbers are in the problems that you're working on. Aside from that, we are still basically doing problems from the last section. Okay. They're just more fun, I think. Maybe you'll think so. All right. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. Wouldn't it be nice if everybody just mailed you a check for the amount that they spent at restaurants? It'd be pretty nice. You'd be richer than Bill Gates. Okay. So, is there something we're supposed to do here? Does it say what is the blah blah blah? Yeah, that's kind of weird. So what we're going to do is try to write an equation for this, and then maybe we'll figure out how much people are spending at restaurants this year, so 2015. Okay? Now, there's a couple of things that we need to talk about. Since 2005, first of all. So, since 2005, that means in 2005, how much time has gone by? What? Since 2005, right? So, in 2005, how much time has gone by? 0 time. So, this is 0 right here. X equals 0 in 2005. Which means in 2015, what will x be? 10. Good. So let's just put that down. In 2015, x equals 10. 10 what? Years. It's really been 10 years since 2005. Oh boy. All right, the amount of money spent at restaurants in the United States has increased about 7% each year. So let's not worry about this problem for now. Let's say you have a job and you make $10 an hour. And I want to give you a raise of 20%. How much money do you make now per hour? So we got to think, okay, we're $10 an hour now, and the raise is 20%. How do I find out 20%? What do I do? Divide, multiply by. Okay, let me ask you this. How much am I making now? How much are you making now? You made $10 an hour, you got a 20% raise. And then your boss says, you're only going to get that raise, though, if you can figure out how much you're supposed to be making now. You going to be able to do that? That's what I'd do. $200? No, you're going to get fired for that. $12? Yes, you would be making $12 an hour. How did you figure that out? 20% we can't work with. We have to turn that into a decimal. What is the decimal version of 20%? 0.2. You move the decimal over 2 places to the left, and you have 0.2. It's almost like we never learned this before. Well, I know we did back in August. Now, if I want 20% of $10, what am I going to do? Multiply 0.2 by 10, that's right. That'll give me how much of $10, or how much is 20% of $10. The word of means what? Multiply. 20% of $10 is 0.2 times 10. And what do we get? Yeah, probably about $2. 0.2 times 10 is $2. So does that mean that's what I'm making now? I'm making $2 an hour instead of $10 an hour? That's awesome. What do we have to do now? Yeah, we have to add the $10 because we were making $10. Now we're making a raise of $2 more. So we got to take the 10 plus the 2, and that gives me $12 an hour. Is that a pretty good deal? So how did we do that? We had $10 an hour, which was 100% of what we're currently making. We have a raise of 20%. So we found out what that raise was, and then what did we do? What did we do? We have 100% of our wage. We got a raise of 20%. We found out that's $2. What did we do to that? We added them together. We added the 100% and the 20% together. So if I take 100% and I add 20% to it, what do I get? 120%, which as a decimal would be 1.2. So I'm now making 1.2 times what I was making before. So if you hear people saying 3 times or 5 times or 1.2 times, this is what they mean. This is how they figured it out. 100% of what we were making, all of it, plus the raise, which was 20%. 100% plus 20% is 120%, which is 1.2. Now I can take whatever I had and multiply by 1.2, and I get my new amount. In this case, my wage. Okay? Now let's take this, which was meant to be an easier problem, and apply it to what we have here. The amount of money spent at restaurants in the United States has increased about 7% each year. So what percent are we actually talking about here? If you spend $100 at a restaurant per year, how much money are you going to spend at a restaurant the next year based on what this is saying? What? $700. That would be an increase of 700%. Probably not right. $107. Because 7% of $100 is $7. I'm going to spend that same $100 because it says I've increased, plus that 7%, which was $7 for a total of $107. So this was 100% right here. This was 7% right here. So in other words, what percent are we talking about? $107%, which as a decimal would be 1.07. That's right. Now we're working with y equals a times b to the x. This percentage right here goes right there. But it's not going to be 0.07. It's going to be 1.07. The total percent that you are increasing plus the 100% that you had to begin with. So now we have y equals a times 1.07 to the x power. All we got to do now is figure out what a is. What is a? $360 billion. It's the initial amount, the amount you start with. We're starting in 2005. In 2005, $360 billion was spent at restaurants. Now, do I need to sit here and write out 360 with like 85 zeros behind it if that's what I need? No, I can just write 360, but I got to remember that it's billions. So y equals 360 times, in the parentheses, 1.07 to the x power. Now I have my equation. So you need to realize that this easier problem over here, in numbers that we can understand, is exactly the same as this harder problem over here. They work the same way. You're going to be doing things like this your whole life. If you don't do things like this, you probably will be losing out on a lot of things like money and salary, and you'll be spending more money than you need to. So you really need to understand what's going on here. Okay, so we just needed to come up with an equation here, I guess, and that's what we did. So now let's make up the problem and say how much money are people spending, is people spending, I don't know, were people spending in 2015? What do we do? That is 10 years since 2005. That's right, that's why we talked about this. In 2015, that means x is 10. So we're going to plug 10 in right here. So we have y equals 360 times 1.07 to the 10th power. Now there's no way we're going to be able to figure that out by hand. So you got to get a calculator here. What's our answer? Sorry, can you read them again? Times 10 to the 8th? I don't think so. Did you enter in 360 billion or just 360? Oh, you entered in all the zeros? Okay. So what we have here is we've got to move the decimal place over 8 places. So we have 70817. Now move it over 8 places. 1, 2, 3, 4, 5, 6, 7, 8. Pretty sure that's not going to be right. Are you sure you entered in billion? So let's do this. I'm going to erase this. And let's just use exactly what I have written up here. We'll remember in our head that it's billions, and we'll take care of the billions part later. For now, let's just use 360 times 1.07 to the 10th power. Does somebody have that worked out? 0.17, so like 0.2. Okay, so let's call it 0.2. 708.2 what? $billion. So people get around having to write all those zeros down by just writing down the word billion. We understand that a little bit easier than we understand 708, comma, 200, comma, 000, comma, 000. So $708.2 billion. Is that more than we were spending in 2005? By a lot? By a huge amount. Almost double what we were spending in 2005 compared to now. Pretty scary, yeah. So if everybody who went out to dinner sent you $1 each time they did that, you'd have a lot of money. Now that's including like McDonald's and Subway and other restaurants and bars and things like that. But that is a lot of money. The restaurant business is a huge part of our economy. Okay, and then we could use this equation here to estimate how much money we'll be spending in any year that we want after this, like 2025. Something else that is exponential growth is this thing called compound interest. This is a pretty important problem for you in your lives. When you invest money in a bank or like maybe in a account, any account that gains interest, or bonds, like some of you maybe have government bonds that you can't cash until you're 18 or something like that, and they're just sitting there earning interest. They all earn interest using this formula right here. A equals P times 1 plus R divided by N to the NT. Notice that there's like no numbers in this. That's why it's called a formula. We've worked with formulas before. All we have to do on problems like this is understand where to plug in all the numbers that they give us, and then we'll get answers from that. Now the idea of an account that earns interest is the amount of money you have in there earns a certain percentage of the amount of money that's in that account. And then they add that percentage to the money that you have in your account, and now you have more money. And then the next time they do it, since you have more money and the percentage hopefully stays the same, you earn a little bit more money the next time that they give you interest. And now your account grows even more. And then you earn more money the next time. So what happens is, here's your amount that you have now, and then after like a certain amount of time, you have a little bit more money. And then you have more money in your account earning the same amount of interest, so after a little bit more time, you earn a little bit more money than you did last time. And then after another amount of time, you earn more money than you did the time before that. And then after another amount of time, you earn even more money. And then more money. And doesn't that graph kind of look like our exponential growth graph? And that's what happens. If you invest money into an account and let it sit for years and years and years, it will do this. And even if you have just a couple hundred or a couple $1,000s in that account and you let it sit, maybe until you retire, you wind up with a huge amount of money in that account. And then you have lots of money. You don't have to work anymore. It's kind of nice. So we'll talk about that after we get through with a couple of these types of problems. Let me get rid of this graph because I don't want it to get in the way. And here we go. When you invest money in a savings account, the bank will pay you interest on the money in the account. That's the whole idea behind investing money. You probably have parents who are doing that, retirement accounts and things. This is called compound interest. If you're ever getting a loan or you're investing in a bank or you want to open an account, you want to ask them how they do their interest. What is the interest rate and how often do they give you interest? That's called compound interest. If you deposit some money in an account, the new balance will be, so here's your balance right here, the new balance will be P, which stands for the initial amount. Actually, in banking terms or in money terms, P stands for principal. So let's put that down there. Not like the principal of the school. The principal in money means the amount of money that you have deposited, the initial amount. Then in the parentheses we have 1, don't need to explain that one, plus R. R stands for rate. The annual interest rate is R, but they'll give it to you as a percent. You want to turn that into a decimal, and we've just talked about how to turn a percent into a decimal. How do you do it? Move the decimal 2 places to the left. If you need to write that down because you can't remember it, then write it down right here. In parentheses, move the decimal 2 places to the left. Then it's expressed as the decimal. Now that's r divided by n. N is the number of times that the interest is going to be compounded, meaning the interest is going to be given to you per year. If they're going to give you interest 4 times per year, then n is 4. If they're going to give you interest 365 times a year, then n is 365. So the number of times interest is compounded per year. And finally, we have an n up here. This n here is the same as this n here. So whatever that number is will be the same as that number. And then we have this t, and of course t represents time. And time is measured in years. Now, that's all straightforward stuff. The only thing that's kind of confusing in problems like this is this number n right here. N is the number of times that they're going to be giving you interest, the number of times that they're compounding your interest. There's key words in these problems that will give away n. You got to watch for them. The word yearly means once per year, so therefore n would be 1. The word annually is the same as yearly. They mean exactly the same thing. So again, n would be 1. Quarterly, like the 4 quarters of a dollar or the 4 quarters of a football game or basketball game. Quarterly means 4. So therefore, they'd compound your interest 4 times per year, which means like once every how many months? 3 months, yeah, because there's 12 months in a year, 4 times a year, that would be once every 3 months. Monthly, how many months are there in a year? 12 months in a year. Therefore, n would be 12 in that case. Weekly, how many weeks in a year? There's 52 weeks in a year, so they would compound. They give you interest 52 times per year. And then daily, of course, 365 days in a year, so they would give you interest 365 times in 1 year. Which one sounds the best out of all of these? Yearly? Remember my example. Every time they give you interest, you have a little bit more money. And pretty soon it starts to take off. If they're only giving you interest once, then you don't have this look. So the more they give you interest, the better. So if you're looking for an account somewhere that you want to open up, and you're like, oh, I don't know, maybe I'll go with Bighorn Fed over Security State Bank or something. I don't know. Take a look at their interest rate. If they have the same interest rate, then take a look at how many times they're going to pay you interest. Maybe Security State will pay you quarterly interest, but maybe Bighorn Fed will give you monthly interest. Which one are you going to go with then? The second one, because it's going to give you monthly instead of quarterly. So this is very important to you in your lives if you care about making more money. And really, I mean, who doesn't care about making more money most of the time, right? He does care about making more money, though, trust me. Okay, so now that we know all that stuff, let's see if we can solve a problem. It says, suppose that when your friend was born, and maybe some of you are in this situation, your friend's parents deposited $2,000 in an account, and that account paid 4.5% interest compounded quarterly. What will the account balance be after 18 years? So when your friend turns 18, the parents are going to hand this bank account over to you. So let's pretend that it's you. You were given this account. It started out with $2,000 in it. A lot of money, right? Not really. Usually people think $2,000 is a lot of money. You can do a lot with $2,000. But now you let that account sit for 18 years. It's going to sit there and gain money. So let's figure out how much that thing's going to be worth in 18 years. To do that, notice that it said compounded quarterly. That's a giveaway right there. That tells you two things. First of all, it tells you that we're using that compound interest formula, which was A equals P times 1 plus R over N to the NT power. As soon as you see that word compounded, you got to think that formula right there. It's a giveaway, dead giveaway. Okay, now they tell us all the information that we need to just substitute numbers in and then type them into our calculator and get an answer. It's very straightforward. So what is P? Yep, P is the initial amount, which was $2,000. So we're going to write 2,000, parentheses, 1 is just 1, plus, what is R? R is the interest rate. What is the interest rate? 4.5, but that's percent. So how do I treat that? I got to move the decimal how many places to the left? 2 places. So I go 1 to here. I got to go 1 more, which means I need to put a 0 there. So 0.045 is my R. 0.045. Be careful and make sure that you are moving that 2 places, not just 1. Now I'm dividing by n, and n is what? The number of times you're getting interest per year. We see this word quarterly right here, and quarterly says I'm getting interest 4 times per year, so I'm going to write 4 here. Close the parentheses. Then in the exponent, I have the n again, so I'm going to write 4 again. And then 18. So this is actually 4 times 18 in the exponent, because we're letting that thing sit for 18 years. Okay, so everything is entered in. Now we need to bring up the calculator and type all that stuff in. Okay, so we have 2,000, not 20,000, and then times, in parentheses, 1 plus, and then my rate was 0.045 divided by 4. Now I get out of the parentheses, and I got to raise that to the 4 times, it was 18 years. Press enter. $4,475.53. That's how much you'd be getting the day you turn 18 from your parents from their $2,000 that they initially invested. Of course, you'd have to pay taxes on that, but that's beside the point. So, better than 2,000? For sure. Is it a lot of money? No, you're certainly not going to set the world on fire with $4,400. You might be able to buy a beater of a car or something. But, you know, when you're 18 and you're getting shoved out the door, that's a lot of money, right? That's, yeah, ramen noodles and SpaghettiOs and peanut butter toast. Yeah. So that's a good deal. Interest works for you. It's called putting your money to work. Now that's if you just let that sit for 18 years. But let's say your parents forgot. They forgot to give you this thing. And you discovered that you had this account in your name when you retired. What age do people retire at most of the time?
65.
Like 65. Let's say when you turn 65, the day you turn 65, you find out that you have had this account since you were born. What does that do to my initial problem here? It's exactly the same, except instead of times 18 up here, it turns into times 65. So the nice thing about doing this on the calculator is I can go up and select that, press enter, and now I can make changes. I can delete that 18. I don't have to type all this back in, and just type in 65 and press enter. And now I have $36,664.80. Is that a pretty good deal? That's a ridiculously good deal. So letting money sit for a long time, it takes a while for that money to start building. But look at this, over 65 years, your $2,000 turned into $36,000 plus. Maybe by then that won't be worth that much, but $36,000 now is a pretty good deal. So money that earns interest, especially at an interest rate of 4.5%, which is pretty tough to find these days. Back in the 70s and 80s, you could find accounts that did that. And before then, you could find accounts that had better interest than even that. But if you can find an account that does that, and you can put a huge amount of money in there and let it sit for years and years and years, when you retire, you'll have a lot of money to play with in the end. Buy yourself a Corvette and a RV and go tour the country with it. Maybe not with this amount of money. Or yeah, maybe you could buy ramen. You could just buy the factory. Yeah, there you go. So when your parents are investing money into their retirement account, that's what they're doing. They're putting money in and they're just leaving it alone. And maybe some of you have accounts. Actually, do any of you have accounts that you have money in? Yeah, usually a lot of kids do. That's good, okay? Hopefully you can see that you don't want to touch that money. Your parents are doing you a favor by doing that. And then when you get to be whatever age that you get that account, do your best to let it just sit there. It's hard to do because really you want to go buy Call of Duty 8 or whatever it is that's coming out next. But just let it sit there. Because if you start pulling money away, then this situation right here won't happen anymore. Okay? All right, let's see if we answered the next problem. Suppose the problem pays interest compounded monthly. What will the account balance be after 18 years? So maybe instead of going to Bighorn Fed with this measly quarterly compounding, they go over to Security State, and I don't know, that's probably, I'm just making it up by the way, and they get compounded monthly. So which problem do I need to change here? I got to go back up here to the first problem, because this second one that we did was just make-believe here. Go back up here, select it again. Now this is the original problem, but what's going to change? The 4 changes to a, not a 6, a 12, because it's compounded monthly. So we got to go in here and delete the 4 and change it to a 12. And then go inside, because we had n is in 2 places here. I need to go into the denominator there and change that to a 12, and then I press enter. It's not that much more. That's right. But it is more. And more is better when it comes to money, right? Unless you're paying more. More in your account is good. Don't disagree with me, because I know I'm right. Okay, now with this situation, let's say that they let that thing sit. They forgot to tell you, and now it's going to sit until you're 65. So we go back up here, select that one. I'm keeping the compounded monthly, and now I'm going to change the 18 to 65 again. And now instead of $36,665, I have $37,065. So it's $500 more. That small difference winds up giving me another $1,000 over time for when I retire. So it doesn't seem like a lot of money, but it is a lot of money over a long period of time. So that's why you want to shop around. So even a small difference in an interest rate, or something as subtle as compounding quarterly versus compounding monthly, any of those things can have a huge impact on how much money you have down the road when you turn 18 or when you retire, or when your kids are born, or whatever it is that you're doing, okay? So those little subtle differences have a huge impact, and that's why most of your parents, when they are investing money into their retirement, take a lot of time and think about where they're investing their money to make sure that they get the biggest, like what we say, the biggest bang for their buck, so that when they retire, they have as much money as possible. So you guys can do that sort of thing too. And it even can start now. You can start thinking about that now. Okay, so the balance here after 18 years, that was $44.89. Point something. What was the point? 0.08. Okay. And on this one, the answer was what? The original answer that we had. I just want to get the answer down so we have it. So start over, what was it? 4475.53. So in this case, after 18 years, you only gain an extra $13. But you know what? That's like 3 gallons of gas or something. That's a pretty good deal. No problem. Right? A couple of cheeseburgers at McDonald's. It's worth it. Okay. So that was exponential growth. Now we're going to talk about exponential decay. So now our money is not growing. We're not even talking about money here anymore. We're talking about things decaying over time. Things that decay over time are like radioactivity, sometimes population if there's a sickness, like in a zombie apocalypse, that would probably be exponential decay. Let's see, the examples that we have here, obviously population. There's other things that also decay like this. So, here we go. Trees. Yes, they do actually. Exponential decay can be modeled by the function, and what do you notice here? It's the exact same function. Yeah. But this time A is positive. It was last time too. But B is a fraction between 0 and 1. That little difference causes decay instead of growth. So the base B, this number right here that you see, is called the decay factor. And you just do 1 minus the percent rate of change as a decimal. Just like in the last problem when we're doing growth, we did 1 plus the percent rate of change. Here we're doing 1 minus the percent rate of change to get us below 1, between 0 and 1. So again, the initial amount is still sitting right here, that A. Whatever we start with, that's your number. And then the base is the decay factor, and we still have that x power sitting there. Our graph looks like this. Rather than looking like that with our growth, it looks like this, and we're calling that decay. Okay, the population of a city is 45,000 people, and it decreases 2% every year. If the trend continues, what will the population be after 15 years? So if we're losing 2% every year, then we can think of that as saying, well, how much of the population is remaining every year? If we're losing 2%, then how much is remaining? It'd be 98%, right. And that's where the 100 minus the percent rate comes from, or 1 minus 2% would be 0.02 as a decimal. 1 minus 0.02 is 0.98, which is 98%. So take 100% minus 2%, you got 98%, which means that we're working with 0.98. And that's our base. We start with 45,000 people. So what's my equation going to be? Y equals times 0.98 to the x. That's right. Right? Yeah, that's it. Okay, now is this number right here between 0 and 1? Yes, and it's supposed to be. So always check that. Is this number right here what I started with? Yes, which is supposed to be. Okay, so what will the population be after 15 years? What do we got to do? Plug in 15 for x. So we have y equals 45,000 times 0.98 to the 15th power, because 15 goes in for x. And then we just type that into our calculators. So that's 45,000 times 0.98, the exponent button, and then 15 years. And we press enter. There's only going to be 33,235.6 people. Can I have a 0.6 people? No. So what am I going to write? Well, it's 33,235.6. So I'm going to write 33,236 people. There's my answer. Round to the nearest person. You can't have a decimal point of a person. Nope, doesn't work. Doesn't work. There's no half of people. So, is the population getting smaller? Yeah. It says that the population is decreasing, so I better see a smaller answer here. It's only decreasing by 2%, so it's not like everybody's going to leave the town instantly. It's going to happen over time. So let's take a look at this last one here. What is the decay factor in the function y equals 17 times 0.2 to the x power? What's the decay factor? 0.2? Yeah, that's it. It's the number underneath the exponent, which is this number right here. Up here it said the decay factor is 1 minus the percent rate of change. Well, that just gives me this number right here. So 0.2 is the answer for the decay factor. on that problem. Okay, that was the whole section all at once. You need to know two formulas. Growth and decay are the same. They use the exact same formula. The difference between growth and decay, though, is that growth will have a number for b that is what? Growth will have a number for b that is bigger than 1. Decay is the one that has a number that's between 0 and 1. The other formula that you need is the compound interest formula, which was, well, let me go back to where I had it exactly written down. This one right here. A equals P times 1 plus R over N to the NT power. Compound interest. If you see that word compound, you're using this guy right here. So on the homework, there's plenty of problems that are using this and the other two. You can do the whole section now.